Welcome everyone to today's Edison Electric Institute webinar on harnessing predictive analytics to prevent cable failure. My name is Vanessa Ferrero and I'm an analyst for international programs at EEI. Lawrence Jones, our vice president, couldn't join us today, so I will be moderating today's discussion. Joining me are Busayo Akinloye and Kevin Wan from ENMAX, who will be discussing how they are working to improve reliability and reduce outage costs. Before we get started, I want to go over some housekeeping items and remind everyone of EEI's compliance with antitrust laws. As you all know, EEI and its members are committed to full compliance with all laws and regulations and to maintaining the highest ethical standards in the way we do business. This commitment includes strict compliance with federal and state antitrust laws. Throughout this session, we encourage you to join in the conversation by submitting questions using the chat feature. The webinar presentation and recording will be made available to all attendees after today's session. As you all know, reliability is critical when it comes to the energy grid, and electric companies are held to high standards to ensure customers receive safe and reliable energy. As we look to the future of the electric power industry, companies are leveraging new tools and technologies such as Internet of Things, artificial intelligence, and machine learning to improve operations and increase efficiency. ENMAX's work to proactively identify underground cables at high risk of failure is an example of the industry's continuing innovation. Now, I will turn this over to Busayo and Kevin to share their exciting work with us.
Okay, thank you, Vanessa. Thank you for the introduction, and thank you everyone for joining us for this presentation, where we will be discussing the work we have done in equipment failure susceptibility ranking and how it is helping ENMAX through database decision-making. Next slide, please. So in this presentation, we'll provide a high-level introduction of ENMAX and a brief introduction of ourselves. We will then get into discussing the different phases of this project from start to finish and end off by sharing our conclusions and answer any questions you may have. Next slide, please. So getting right into it, ENMAX is a vertically integrated utility responsible for making, moving, and marketing electricity throughout all of Alberta, Canada. ENMAX owns and operates generation and distribution of electricity in and around the Calgary, Alberta area in Western Canada, supplying power to more than 600,000 customers through 43 substations. And as the wires owner of the distribution system in Calgary, we rank among the top 25% of most reliable utilities in Canada. And next slide. We'll have a brief introduction of ourselves, where Busayo and myself are members of the operations planning team on the power delivery side of ENMAX, and the team is heavily involved in providing the system control center with real-time and short-term engineering support for the transmission and distribution system. We perform transmission and distribution outage coordination studies. We look after power quality and investigations of that nature, and we're also looking after the outage reliability statistics. And because we're at the heart of every outage, we hear and see the trends in the outages occurring and can provide insight to other groups. Next slide, please. Now to talk about the project. Overall, this project was split into 5 phases, starting with problem framing, where we identify the issue and determine our preliminary goals that we had set, to then data acquisition and data exploration to better understand the issue with the data we're having and determining how we can meet the goals we set. With data exploration, we also had data transformation to set it up for model development, where we will share the model development phase, followed by results and validations to come to our conclusion. Next slide, please. So starting with problem framing. As part of the operations planning team, again, we focus on near real-time and short-term operations for both the transmission and distribution system. And again, with understanding the reliability analysis and reporting, we understand that majority of the unplanned outages we experience are on the distribution system, where we have a mix of overhead and underground distribution. And majority of the new distribution developments have been underground cables in the past half century. So that's where our focus is heading towards. Next slide, please. So one area of concern we've had in the past few years is underground cable faults, also known as cable failures. And some of the reasons why we're focusing on underground cable failures are because they've become the highest contributing outage cause to total customer outage minutes and total outage frequency, also known as SAIDI. Cable failures are a top contributor to total operation and maintenance costs. And to meet high customer expectations, where there's a lower tolerance for long outage durations. These are the reasons why we focused on cable failures. And on the left-hand side of the slide, we have an example of the ENMAX underground distribution system, where we have highlighted two portions of an underground radial distribution loop in blue and green, and both have protective fuses upstream and also a common normal open point, so that if one side of the loop experiences a cable fault, the fault would be located by a crew, isolated, and then customers would be restored by closing the normal open point and replacing the fuse. And essentially here is where if multiple cable faults occur within a short amount of time before repairs are made, this is where we have longer outage durations that repairs have to occur first. Next slide, please. And so there's a lot of speculation as to what's exactly causing these cable failures. And there's common examples of these causes, which include cable insulation degradation, possibly due to exposure to heat, moisture, or dirt, conductor corrosion, again, possibly due to moisture or water ingress, excessive loading causing stress and heat on the cables, age causing natural deterioration, and also possibly manufacturing defects. And on the right-hand side of this slide, we can see a field crew performing splice repairs on a cable fault with de-energized cables. And in Calgary, we experience extreme weather conditions in both extremely cold winters, but also hot summers. And the pictures showing how challenging it can be for crews as it's snowing, and factors such as these potentially increase the restoration time. Next slide, please. So for the problem framing phase, we have identified that cable failures is our focus, and understanding the ENMAX system, knowing our data, we know that moving on in this project, we have to aggregate cable section attributes to be represented at a fuse level. This is because we have hundreds of thousands of cable sections to analyze, and realistically, to be optimal with analyzing them, we have to group them and analyze them at a more reasonable upstream level. So that's why we've brought it to approximately 10,000 fuses at an upstream level. And so with all this in mind, we had set our goal of using data analytics to rank underground distribution cables based on failure susceptibility. Next slide, please. So we then move on to data acquisition, where we had to gather and combine different data sets to be consumable in the future phases. Next slide, please. And so starting with our GIS asset record management system, this is where we had all of the physical attributes maintained by the GeoWarn group to have all the physical attributes to underground cables, and they're stored in a central system so that we have all this physical attributes such as burial method, conductor material, neutral material and type, and also cable length for each cable. So this is all the data sets we're combining with also the outage management system, where we are able to understand the history of outages on these cables, number of previous faults experienced, and customers impacted, which also kind of provides more information to the loading. As well, we also used external data sets, such as our municipality's open data portal called Calgary Open Data. And here we used a water body map to calculate the distance to the nearest body of water for each fuse as a feature to our model, which is something that we'll get into a bit later on. And also we brought in weather data, such as temperature and precipitation, as those are very, these are things that fluctuate throughout the year and can make a difference. Next slide, please. And from here, I'll pass it on to Basayo Kimloy.
Thanks very much, Kevin. I hope everyone can hear me. So one of the things that Kevin mentioned was the fact that we aggregated up to the fuse level, because due to some data limitations and also due to some, due to the fact that we wanted to keep our data sets manageable. And so as I go forward and when I talk about fuse outage or fuse replacement, what I really mean is every cable section downstream of the fuse is what I'm talking about, aggregated up to the fuse, protective fuse device. So if we go straight into data exploration, next slide, please. We started with what we had in our databases and our data sources, and we had a lot of information to work with. So we had to go through extensive feature selection process and data cleaning, data merging, to really find out what we're going to need in order to create a really good model. At the end of the day, we ended up having about 47 feature columns going into a machine learning model. But for the sake of this webinar, I will be talking about just 4 of those that I think are pretty interesting to talk about. So if we go to the next slide, please. We're going to start with the cable age. Here I have 2 graphs. The one on top shows the demographic distribution of our underground cables versus the actual outages in 2019. So looking at the top graph, the blue line graph shows the demographic distribution based on installation year. So for example, cable installation started in the 1960s and then ramped up to its peak in the 1980s and then sort of came down and became steady around into the 2000s. But if we then look at the 2019 outages, which is the blue bar graphs that you're seeing, we see that majority of the outages that occurred in 2019 occurred on the guys installed between around 1970 to the 1990s. So what we're seeing here, we saw this year over year to be very consistent. So what we're seeing here is that the older assets are the ones failing. It could be due to vintage, also be due to the age of the cable. So the graph below that, which we decided to look into a little bit more, is the survival curve for our cables, underground cables. On the y-axis, you have the survival rate from 0 to 1, 1 being a survival rate of 100%. On the x-axis, you have the age from 0 to 50 years. As you can see, at an age of about 10 years old, the cable is close to about 90% survival rate. But then if you come down to about 30 years old, you're down to about 65%. And then there's a steep decline from there on as the cable gets older. So this sort of correlates with what we're seeing on the top graph, that it's the older guys that are failing. So definitely we realize age is a factor in when a cable will fault or whether or not a cable will fault. So if we move on to the next slide, we'll take a look at cable injection. Now, cable injection is the act of injecting a compound into an underground cable in order to extend its life. And we wanted to look into that practice to find out if it's really effective and when it's effective and up to what age. So we decided to create a survival curve for both the injected and the non-injected cables in our system. And what we found by looking at this graph is the orange line is the orange graph. It shows the survival curve for the injected cables, while the blue graph shows the survival curve for the non-injected cables. As you can see, the survival rate for the injected cable is slightly better than that for the non-injected cable. However, that only lasts up until about 35 years of age, where you see that there isn't really an advantage for injection at that point. So this gave us a little bit more insight in the practice of injection and using that into a model of whether or not the cable has been injected in the past or not, and the age at injection and all that. That tells us the efficacy of the injection itself. So if we move on to the next slide, please. We're going to talk about distance to water. Now, this is a very interesting one that we decided to look into. Calgary is full of water bodies, lakes, and all that. And we've always had got some feedback from the crew about investigating the impact of soil moisture to the corrosion, cable corrosion, or cable faults. So we decided to dig into that for a little bit. And what we have here is a 3D graph showing on an annual basis, which here on the x-axis, and the distance on the y-axis in meters. And the z-axis, you have the average amount of faults per bucket of distance. And what we're seeing here is that as the cable is farther away from the water body, it has a higher chance of failure relative to the other cables in that year. This was quite interesting for us, but something else we decided to look into was that, correlation doesn't imply causation. There could be a middle factor such as age. It could be that the older cables are farther away from the water, depending on when the city of Calgary started building out. So we decided to normalize for age, and what we found was that we kept seeing the same trend of farther away from water higher chance of failure or higher number of failures. So that was something that was quite interesting to us. So thought I'd show here. So if we move on to the next slide, one of the feedback we also got from the crew members, field crew, is that they always seem to come back to the same location over and over again once just after a previous fault. So we decided to look into the theory that if a cable section fails and there's a huge draw of current to the ground, then how does it affect the nearby cables? Does it stress them out, hence pushing them closer towards failure? So we decided to plot the number of previous failures to the average amount of failures per bucket. So what we see here is that as the number of previous failures increase without replacement of the whole cable length, there's a higher chance of failure again on the same section downstream of the fuse. So that's what we saw here, and we decided to use this in our modeling process. So if we move on to the next slide, please. Now I'm gonna jump a little bit into ranking. So if we move on to the next slide, ranking isn't a very typical machine learning algorithm to go to. Usually it's, for machine learning, it's regression, classification, or clustering for investigation. But if you're working with some specific kind of problem statements, ranking lends itself perfectly. So for example, if you're working with large data sets, and you're working with limited resources and other priorities desired, I'm sure a lot of us can relate to that, ranking really is useful. So let's assume you have 1,000 assets and you have just a limited amount of money to replace the top end assets that you can replace or work on. Ranking will give you a way to be able to choose which assets are worst off in your pool, to be able to determine how to effectively spend your money. So that's where ranking sort of lends itself as compared to like regression or classification. Some very common applications where ranking is used is in search engines to rank documents or links based on your search phrase, fraud detection, employee retention modeling, and hierarchical decision making. So these are some of the common applications of ranking. So if we move on to the next slide, please. Before we talk about the model creation process or the data transformation, we decided to show you what the visualization is for displaying the results that you're going to be seeing in a couple of slides down. What we have here is the ranking visualization showing, for an example, 10 transformers, transformer A to J, where transformer A is ranked 1 and transformer J is given a rank of 0.1, 1 being the worst off of the 10 transformers and J being the best transformer in the pool. So having something like this and then trying to show your validation result on top of that, if we move on to the next slide, then we see that to show the actual failures and compare your ranking to actual events, what we did is that we stacked the actual failure on top of the ranking. So for example, transformer A was given a rank of 1 and experienced a failure of 1. Transformer B was given a 0.9 and experienced a failure of 1, and so on. So in this case, this is a best case scenario where all the transformers, all the assets that we ranked at the top of the rank experienced a failure. If we move on to the next slide, we see what the worst case scenario would look like. So the best case is if all the clusters of the actual faults were on the top of the rank. If the model doesn't learn anything about your data set or how to rank properly, then that means that in the worst case, all the assets ranked on the lower end will fail. That means that there isn't really a learning on the part of the model. So this is just to give you an idea of the visualization you're going to be seeing for our validation results, just a couple of slides down. So if we move on to the next slide, please. Now we're going to talk about data transformation because the algorithm could only take data in a certain format, and that is the MOQ format from Learning to Rank research by Microsoft. So if we move on to the next slide, we'll talk a bit about that. So first we began with our static attributes of our fuses. Now remember, when I talk about a fuse, I'm talking about the cable section downstream of it aggregated up to the fuse. So we start with the static attributes of our fuse, and then we go on to the outage information from our outage database. So the static attributes are basically for each fuse, you have the customer count, length, install year, distance to water, and other features. And then for the outage information, you have all the events depending on which fuse failed or which fuse experienced a fault. So for example, in January 2007, fuse 9 and 6 experienced a fault. So if we move on to the next slide, then we'll start talking about how we format our data to be able to create that MOQ format that is required for our algorithm. So what we did was to split our data set into a monthly model. Now we have an annual model, but we also create a monthly model. So here I'm showing the monthly model, how we created the monthly model data set. So what we did is that we split our outage information into based on month. So for January 2007, fuse 9 and 6 experienced an outage. That's given a query of 1. And then basically what we did was get a replica of the static attributes, but then fuse 9 and fuse 6 were given an outage count of 1, while the rest had an outage count of 0. And then in the next month, February, fuse 4 and 8 were given an outage count of 1 in query 2, and the rest were given an outage count of 0. And then on and so on, and in March, fuse 1 and 5, outage count of 1, query 3, and the others outage count of 0. So we continued this iterative process until we got to July 2019, which is when we worked on this project. So if we move on to the next slide, we'll see what the whole, just a screenshot of what the data set looks like. So once we've gone through that iterative process of creating those queries, we ended up having about 139 queries from January 2007 to July 2019. Some months we didn't have some faults in some months, so it's not really the number of months, but for each month that had an outage, we have 139 queries. So this is sort of like a screenshot of the test set that we have. The first column there shows the relevance label, which is the outage count for each fuse in the query. The second column shows the query ID of 139, and then each column after that shows the number of features preceded by an index. So for example, you're seeing here that the first row has a number of customers of 11 and a length of 52.23. So each column is a feature on its own. And as I said earlier, we had about 47 features in total. So if we move on to the next slide, we're gonna begin talking about the model development process. Next slide, please. So what we have here is a simple workflow of the training process and test process. So we started out with a transform data set, which is what we just talked about. And then we split that into a training data set and a test data set. Now the training data set went through a training process that created a machine learning model. And then to find out if the model can really generalize over all other unseen data sets, we tested out the test data set, which was kept apart using the trained machine learning model. And then we compare the actual results of the test process to the actual results, of the test data set. So we'll move on to the next slide. We'll see how we split our train, validation, and test data set up. So for the annual model for 2007 to 2017, we used that for our training and validation, which were queries 1 to 11. And then for our test data set, we used 2018 and 2019, which were queries 12 and 13. I'm going to be showing results for validation, test results for 2018, 2019 very soon. So next slide. Just a little bit more about the model development process. The model was developed using Python programming language. Now I know there's some discussion between R and Python, which one, what language is the best to use. For us being power system engineers, we've always used Python for automation and power system studies. So it was very easy to transition into Python for data science. So I believe R has a lot of the libraries, or all the libraries that we used for this project. So this can definitely be replicated using R. We made use of some open source libraries such as XGBoost, Pandas, and NumPy. And this model was created with in-house expertise, basically combining subject matter expertise in the electricity industry and subject matter expertise in data science and machine learning. In total, we created 2 models, one monthly model to give us ranking on a monthly basis, and then an annual model to give us an annual ranking of our cables. So next slide, please. So just before we dive into our test results, I'm going to talk very briefly about the cost function for ranking. Similar to classification, which has F1 score, precision, or recall, or regression that has RMSE or MAE, ranking has 2 main cost functions. The first is mean absolute precision, and the second is normalized discounted cumulative gain. Now we decided to go with gain because it gave us best results based on our experimentation with those 2 cost functions. Depending on your data set or depending on your use case, you might find the mean absolute precision giving you the best result, but in our case, the cumulative gain gave us the better result. So we decided to go with that. So for the cumulative gain is between 0 and 1, 1 being the best case scenario for your ranking case, which you're seeing on the left-hand side, and 0 being the worst scenario case, meaning that your model didn't learn anything. And all the cables ranked lowest are the ones experiencing the failure. So that means the model isn't able to rank properly based on susceptibility to failure. So next, now we'll go into the model validation results. So I'm going to start off with the monthly model results. I'll be showing just 1 month for this, but we can have discussions about more months later on. So if we move on to the next slide, just as a reminder of what you've been seeing is this is similar to the graph I've been showing, just that the fact that we have a lot more assets. We have about 7,500 fuses here being ranked. So the teal color, the teal color you're seeing are actually bar graphs, but they're really squished. And on top of that, we have the actual failures based on our validation results. So if we click to the next slide, please. What we're going to do is that we're going to zoom in to the top part of that ranking to show those are actually failing. So as you can see here, so in that month, this specific month, we had 5 failures. As you can see, that 4 out of those 5 were on the top, highly ranked fuses, which is what we expect, which is what we want. Means that our model is able to rank in a very good fashion, and that's what we want. So we had similar results for our test months, but I'm just showing one now. But so what I'm going to do now, I'm going to pivot into the annual model in the next slide, and then I'm going to show the 2018 and 2019 validation results. So if we move on to the next slide, please. So for the 2019 year, as for the 2018 year, what we can see here again is that we have the ranking entail, and then we have the actual outages that we have compared against. And we can see the cluster of the actual outages to the top of the ranking scale, which is what we want. We ideally want everything at the top, but yeah, the model isn't perfect. That's understandable, data limitations and errors. So we have some that are on the lower side of the ranking. But if we click on the next slide and we zoom in to the top part of the ranking, we'll see that a lot of our highly ranked fuses experience 1 or more faults. So for example, the top ranked fuse faulted 4 times, or 4 sections faulted downstream of that fuse, and so on. We had a 1, then a 3, and so on. So really, the goal is to have majority of the faults captured at the top of the rank, so that if you're, for example, replacing, if you have a capital budget and you need to replace some cables for the year, you would know where to start from, and hence preventing cables that would have occurred in the future. So if we go into the next slide, what I decided to show before going into the 2019 results was a baseline model. Our baseline model is what we would typically use for determining which assets needs to be replaced, and that is age. That's a very typical, feature to use. The older the asset is, the more likely it will fail and should get replaced. Well, so what I did here was that to normalize the age and rank it based on age, and then compare the results of the age rank to the machine learning rank to sort of see if we're better off with machine learning. And what we can see here is that we can see, we don't see a huge cluster of defaults on the top of the rank. So that means that the older guys, like the older assets, aren't necessarily the ones failing. Age isn't the only feature that you need to consider when you're considering asset failure. I believe if you go down the rank, to get to your first fault, you're gonna have to get to the 80th asset. So if you invested on replacing the older assets, you're really not preventing any outages in the future. So if you click to the next slide, so this is what it looks like for the same year using machine learning ranking. As you can see, again, there's a huge difference. If you click to the next slide, I put it side by side, and then you can see the huge difference between using machine learning and using just age-based ranking. You can see that there's a cluster towards the top for the machine learning ranking, while for the age, it's not really, you don't really capture a lot at the top. So this is just to compare and see that there's a lot more factors to consider that the machine learning takes in: burial method, age, weather conditions, loading, cable type, neutral type, cable condition, injection, and all those kind of features in one model. So moving on to the next slide, we're going to zoom in onto the top of the 2019 results. Again, we see that we capture a lot of failures at the top of the ranking, showing that, yeah, if we started replacing based on this ranking, we would have prevented a lot more failures in the year, in the coming year. So if we move into the next slide, please. So looking at 2020 so far, we've had a bit of clusters towards the top of the rank. We are monitoring the progress as the year comes to an end. We're still experiencing some cable faults, and I hope we don't get more, but I'm sure we will get more cable faults before the end of the year. If we move on to the next slide, we'll see what we've had so far. Just zooming into the top of that ranking scale, we see that the top ranked cable fuse has already failed 3 times this year already, and then we've had a couple more failures at the top, and we're monitoring the gain of this model as the year comes to an end, to see if retraining is required or if we need to look into more features or find better ways to improve the model gain. So that's the last of our validation results. If we move on to the next slide. In conclusion, we've been able to identify high-risk cable sections, allowing for proactive mitigations and replacements. As a result of the analysis that we've just done here, we've developed a reliability monetization model that has enabled us to better forecast cable failures and its impact on our reliability. And we've also gone into translating the forecasted impact into actual costs, whether proactive or reactive. One thing that we've done with this is we've influenced how we focus our capital spending. Now we sort of consider the ranking here plus some other factors to determine which assets need to be replaced. So we're able to optimize our spending while reducing the impact of cable failures on reliability. We've gained predictive insight into the state of our system. And one thing to mention is that this analysis can be expanded to other asset classes: breakers, switches, transformers, distribution of substations, and even also problem statements that don't have to do with the electricity utility industry. I mentioned a company using a ranking algorithm to rank employee flight risk. And it's very controversial, but it's been done out there. So that's sort of like an interesting use case. As always, we are open to peer comments and feedback. And yeah, I hope you found this useful, and thank you for taking the time to hear us speak. Back to you, Vanessa.
Wonderful. Thank you both so much for such a thorough presentation, sharing the process that you went through to create your model. I know as a quantitative nerd myself, it was really interesting to see how you visualized everything and how you actually went about setting it up. I'm going to let us be visible now. Wonderful. So we have been getting quite a few questions in, and for anyone who hasn't added questions, please feel free to add them as we go through the Q&A session. I wanted to start off first maybe with, your model includes a lot of variables that could affect cable failure. You mentioned cable age and previous outages, and from your 2019 comparison, we see like clearly it's providing a ranking that's more accurate than just cable age. Do you know which variable has like the biggest effect on making the model so much more accurate, or is it just the combination of all of the different features that you've been using?
Well, we used some feature importance algorithms to find out which were the top 5 features. And for the monthly model, we found age definitely was on the top, followed by temperature, followed by loading, and burial method. Injection was a factor also, but it wasn't in the top 4. But I believe it was a top 5, if memory serves me right. But it was age, temperature, burial method, and loading.
Cool. We had a question from the audience asking if your cables are buried in conduit or just insulated cable at a certain depth.
So in the ENMAX system, there's a mix of both duct banked, so in conduit, as well as direct buried. I would say majority of the older installed cable are direct buried, and I believe majority of the issues are around the direct buried. Conduit is, it's been pretty helpful.
Yeah, we did some analysis regarding burial type to look at the survival rate for each based on burial method, and we found that direct buried had the worst survival rate of all our cables. So yeah.
Okay, I wanted to ask a bit more about the distance to nearest body of water. First, I guess, how did you calculate that distance? And then I have some follow-ups too. So.
For sure. So I can speak on that. So for the nearest body of water to fuse distance, that's something that, again, going back to the start of it, that's always been a speculation that we've heard from different teams and the crews. And so to really test that, we found the water body maps, and we took essentially open source tools. We used Python and GeoPandas to relate the different assets to the nearest distance. And all using Python, that's how we calculated the distance.
Awesome. And have you been able to do more work to explain why there is that relationship between the distance to water and the cable failure, especially since you showed, the further you are from water, that seems to be increasing it. Has ENMAX started, looking into why that is?
So that's something that we're definitely looking into. We're looking into some other middle features that we believe could give us that correlation. So I talked about age. Now, we're looking into the vintage of the cable, trying to normalize all those other features to see if the trend is still consistent. But we are seeing, based on age and vintage, cable vintage, that the trend is consistent, that the farther it is from water, the higher the chances of failure, which again is sort of counterintuitive, because you would think that if it's closer to water, the corrosion level will be higher. But again, I guess it depends again on the burial method. So there are a lot of intermediary factors that would come into play with that. So yeah, that's why we didn't really think that it was a direct link between distance to water and the cable fault.
Okay. Yeah, it'll be interesting to see what you find as you dig into that a bit more. Yeah. I know you mentioned there are 47 features in the model, which seems like a lot. Were there any variables that maybe you weren't able to include or couldn't include that you think, that you would have wanted to, but maybe you didn't have all the data for it, or anything else to make the model stronger? Yeah?
Yeah. Oh yeah. We had a lot. We went through a couple of iterations of what the model should include or should not include. So we started out building the model for cable sections rather than aggregating up to the fuse. But we didn't have a lot of information regarding the exact location of the fault. So the cable on which section, GIS section, failed. So we had to aggregate up to the fuse And as a result of that, you would lose a lot of accuracy in your data. So definitely the exact location of the fault by lat long would have been very helpful. For the annual model, for example, we couldn't use weather information because it's difficult to capture weather information for a whole year in just one line. So yeah, there were some, those were just some of the features that we wanted to use, but we couldn't.
Yeah. Did your model consider like looking at the average congestion on the lines as a variable, or some other measure maybe of how much like the cable is being used? Or
Yes, we did. Based on, now we don't have the real-time loading on the cables, but we're able to use, based on some peak study results, we're able to get the peak loading of our cables for both winter and summer, and use that in place of the real-time loading, because it would have been better to know what the loading was just before failure, to know if there was a spike in loading or something, but we don't have that granularity of data. So we had to use the next best thing, which is the peak. Yeah,
of course. I know we had another question from the audience about whether the model can be applied to fault detection for distribution transformers. Maybe have you also worked on a similar model for cables that aren't underground?
Well, you can definitely, depending on the data you have, you can use it for fault detection on other asset classes. So for example, if you look at a breaker, a factor could be number of operations. For transformer, it could be weather for overhead transformer, for example, weather would definitely play a role, then loading would play a role. So those are ways that you could rank your transformer. Now remember, you're ranking it relative to all other assets in that group. So if you're ranking your transformers, your distribution transformers, you're ranking it relative to other distribution transformers. So it will not tell you when the transformer will fail, but it will tell you which one is the worst off in your inventory of assets.
Okay. What was your greatest challenge while working on this project?
Well, I know Kevin, please feel free to chime in on this, but the first was data gathering, getting the data necessary, cleaning it. I would say the next biggest challenge was because this is it's not a traditional way of, I would say, ranking your assets or determining which assets needs to be replaced. Dealing with having to communicate your results or your methodology to stakeholders or to upper management takes a little bit of skill or some communication and ideas around that in order to be able to avoid or overcome skepticism or people not really understanding your model or what you're doing and things like that. But we're able to overcome that and really get our message across that this is the result, this is how it was created and all that. Kevin, I'm sure you have something to add to that.
Yeah, I think in addition to, definitely getting past the skepticism of the results and proving that it's something that we think works. It's also kind of building this path for this project where it's not something that's like a template that you can follow. It's really going outside of the box in certain areas and combining different data that has never been combined before and trying out different algorithms that you don't really get to learn from. It's kind of experimenting and trial and error to come up with these results. So yeah, that's probably the biggest challenge I would see.
I wanted to dig into that a bit more. You mentioned, the communicating this to stakeholders. Like how have you been able to maybe explain this to regulators maybe, or to get any, getting investments improved based off of this model maybe, right? Getting them to really believe in it, I guess.
So being in operations planning, we've been able, getting the results was our own first task. And then the next stage was to involve the other stakeholders who would just need to justify this to the regulator. And we've had multiple meetings. We've been in good discussion with them to sort of show them our results, the methodology, the validation results and all that. And I think the fact that you can show the validation and even give a ranking ahead of time, and they see the failures happening and they see where the failures are on the rank, pretty much speaks for itself. And you don't need to really push further after that. So the results speaks for themselves, really. So I think that has been our biggest advantage, showing that, okay, this is a ranking for 2020. As a faults happen, check where they are in the rank. And so far it's been giving us good results. So.
And I mean, you showed the graph for 2020 so far, and I was wondering right now, are you still testing how accurate the model is, or is ENMAX already using the predictions to do proactive maintenance on the top cables?
So we are.
Okay.
So we are using a ranking to choose which assets needs to be replaced. So the group in charge of that is using this ranking plus a bunch of other factors to determine how they optimize capital spending. Currently, yes.
Do you have any estimates that you could share with us for like the cost savings from using this model, or not yet?
I would say not yet, mainly because it's still a new tool that we're using. I'm sure as the years go by, maybe by next year, we would know, based on a reduction in cable fault, we'll be able to compare the current level to our former projected level, right, and be able to see cost savings, yes.
We had another question from the audience saying, compliments to ENMAX for bringing on machine learning experience into the organization, and wondering if that was a conscious hiring decision to build that internal skill capability, or if it was just a happy accident with recent hiring.
That is a good question. So I would say that we are definitely, our primary task, our primary responsibility is reliability and outage management, and control, supporting the control center. However, being the steward of the outage management system and SCADA and the SCADA data and all that, it's very second nature to have all that data and figure out what to do with it, because we had all that data sitting on our Pi historian and in our databases, and they were used mainly for dashboarding and reporting. But we started figuring out what we could do with that data to improve our reliability, because that is our task. I think that set us on a path of some very, curious minds of learning, and just learning as much as we could to dive into the world of machine learning, data analytics, statistics, and all that. So it was a very natural pairing for, that skill set plus the subject matter expertise that we already had to sort of merge to create products like these. And even moving forward, we see a lot of these products or to help reliability churning out of our team. So I hope that answered your question. I hope that answered your question.
I could also add that like within this group and team and everything, we've been very fortunate that management and upper management has been very supportive in these innovative, I guess, different paths of innovation. So they've been very supportive, and that's how projects like these have been able to progress.
Yeah, I mean, I think it's great because I know the electricity grid can give us so much data, and we have so much historical data, like you mentioned, and so finding ways to use that to operate even better, I think is great, and I'm glad so many companies are doing it. Do you know if ENMAX has a model, obviously not with the same variables, but maybe that you may be working on to predict assets that may be more at risk during extreme weather events rather than just normal day-to-day operations?
That would be an interesting problem case. What I would say again is, so we don't have that model right now, but to create such a model would require having the data for those kind of days, for those weather events. So if you have the data for those weather events, some other factors such as geolocation might come into play. For example, if it's a tornado, if it's a snowstorm, a windstorm, then geolocation and where the storm is happening or what assets are there and their history as regards, similar types of weather would definitely come into play. But with those kind of data available to a data scientist, definitely, I believe that such a model can be created.
Okay. How can this work be used to benefit other electric companies? Are you sharing this model with others, or are you working with other partners to kind of get more people to know how to do this?
So, yeah, Kevin, feel free to chime in this.
For sure. So yeah, this is a project that has been in the making, of course, and we've been very open to sharing, how we've done the project and the results. And yeah, for sure, if any other utility is very interested, we're very up for discussion, very up for open sharing of concepts and how it was all done. So yeah, we're very open.
I think one thing to mention is that all the libraries we use, everything was done using open source data. So there isn't anything that we created ourselves, except the compilation of the code. So that's definitely open for sharing. We're putting it all on the GitHub site that we can definitely share with you, containing the code and the models and the sample data sets that can be used.
Awesome, that's great. And I know this project is really a testament, I think, to the value of data. You can literally calculate the savings from reducing these outage events, and you can see the impact of it. So what do you see as the role of data and AI in the grid of the future?
Yeah, the role of AI in the grid of the future. I definitely think we'll see more and more applications of AI in the electricity industry. Machine learning, or whatever you want to call it, has really been adopted by the fintech industry, by manufacturing industry. But in the electricity industry, we're just beginning to understand and beginning to adopt it. We are seeing a shift of or creeping of data skills into even traditional electrical positions. For example, we're seeing a shift from peak planning, from transmission distribution studies to probabilistic planning, which requires some planning and SME plus data science SME. Now in the future, what we're going to see is a skill change or skill requirement change for a traditional planner, whereby you would require a planner to have planning skills for the power system studies. However, you also need them to have skills in the data science, sphere also. So I think we've seen that shift little by little, and I think that the grid of the future is going to be very complex with all these new technologies coming in, and there's so many variables, customer behavior, customer profiling, EVs, PVs, DERs, and all that. I think AI would lend a good way to be able to understand all these variables and make meaning of them, and give results based on problem statements. So yeah.
You mentioned the skills that that future kind of employees will need to have for the industry. Do you know if ENMAX is working to establish like talent pipelines in those areas, or working with universities or other local groups?
So we have a group that is in charge of this strategy, the Grid Innovation and Strategic Innovation Group. So what they do is to focus on the future of the grid and what requirements, what skills are needed, what kind of people need to be hired, and where the grid is going into the future, and how to prepare ENMAX for that future. So we have a strategic innovation group that looks after this. So I believe ENMAX is working on such strategies, yes.
Perfect. And this will be my last question is, I'm sure that this is only one example of all of the work ENMAX is doing with data analytics. Is there any other, area that ENMAX is looking into that you might want to share with us, where maybe you're creating some models like this one?
So this is just one of the products that we've created using data analytics. We've worked on some previous ones, such as load forecasting, PV forecasting at the customer level. So for each customer, we know what the day-ahead hourly forecast would be. We're also working on some other initiatives, for example, for fault detection, being able to recognize fault signature and be able to predict when a failure is going to happen. Those will require some sensors, which we are working on. And there isn't really an end to the innovation that I believe that ENMAX is capable of. So we do have a lot of innovative projects on the pipeline. And yeah, we are really excited to work on those and share them with the industry as they, as they get done. So yeah.
No, I think that's very exciting, and I'm sure we'll look forward to maybe having you on a future webinar to talk about a new project that you've been doing. So it'd be great to follow kind of your journey as you keep building out these models and data analytics. So, well, Lusayo and Kevin, I'd like to thank you so much for taking the time to share this exciting work with us and for a great discussion during the Q&A. I also want to thank everyone for joining the webinar. We hope you found the discussion valuable, and we appreciate your thoughtful questions and participation throughout the session. We will send out the webinar presentation recording to all attendees, and we look forward to your attendance at our future webinars and virtual events. To continue engaging with EEI international programs and to learn about other upcoming events, please follow us on Twitter and visit our website. I put them in the chat. And thank you so much and have a wonderful rest of your day.
Thank you very much, Vanessa. Thanks, everyone.
Thank you, everyone. Thank you, Vanessa.
Bye.